So we're going to look at some examples of stoichiometry problems. Specifically, we're going to look at different ways in which you can attack these problems. So stoichiometry is the study of the quantitative relationship within chemical reactions. Whenever we look at chemical reactions, we're going to look at a balanced chemical equation. And so we're going to have on our left-hand side our reactants and on the right-hand side our products. And due to the law of conservation of mass, whatever shows up on the left-hand side has to show up on the right-hand side. So one of the first things we ever do when we have an equation is to make sure that these number of particles are conserved. So if we were using this as an example, 2 carbons, we're going to go ahead and put a 2 there. Based upon our hydrogens, 6 on the one side, we'll go ahead and put a 3 here. And the last thing to balance would be the oxygens. Now there are 4 here and another 3 there, so 7. And so one of the things we can do is we can just say that we have 7 halves of the oxygen molecule. Some people do not like having the fractions written there. When we're talking about moles, it does not matter. But if you would prefer to have it as whole numbers, you could go ahead and multiply everything through by 2, and so you would end up having a coefficient of 2 in front of the ethane in this case, a 7 in front of the oxygen, 4 in front of the carbon dioxide, and 6 in front of the water. And so we have a 2 to 7 to 4 to 6 molar ratio. Now when we do a stoichiometric calculation, we're relating amounts of these substances to each other based upon this chemical equation, this balanced chemical equation. So an example of a simple stoichiometry problem would be if you were given this equation, you might be asked how much CO2 and let's go ahead and say how much water would be produced when we have a starting amount of 2.5 grams of ethane. And again, this type of reaction here, since we're reacting with oxygen, would be referred to a combustion reaction. So we're combusting the ethane. Well, since it is a simple equation, or a simple stoichiometry problem rather, we would go ahead and say, well, we've got 2.5 grams of ethane. And the first thing we would do is convert it into moles. The relationship between these substances, the balanced chemical equation, is in terms of moles. So the first thing we always have to do is convert it into moles. So the way we do that is to use the molar mass of ethane. 2 carbons, 6 oxygens, molar masses added up on the periodic table give us 30.07. The second part, the second thing to do is to relate the two substances together. So we're going to do a mole to mole ratio. We're trying to go from the ethane, which has a molar ratio of, or has a coefficient of 1 in our balanced chemical equation. That is in the top one, and we have 1 mole of that, and if we have 1 mole of that, we have produced 2 moles of carbon dioxide. The last step is to convert it back into grams, and so often we're worried about how much, so we're talking about how many grams of CO2 is being produced. So the molar mass of carbon dioxide, 1 carbon and 2 oxygens added up, is 44.01 per 1 mole. And so when we plug all these numbers into our calculator, we end up with 7.32 grams of CO2 are produced. We said we were also interested in how much water was being produced, so the problem starts off the exact same way. We start off with the amount of ethane, we convert to moles, but instead of doing a mole-to-mole ratio to carbon dioxide, let's go ahead and look at our 1 to 3 ratio of ethane to water. So 3 moles of water are produced. And the last step of converting it into moles, use the molar mass of water. And if you do this calculation, go through, you end up with 4.49 grams of water produced. Let's say that the problem was a little bit more complicated. Now, in the previous one, the simple problem, when they say how much carbon dioxide and water is being produced from 2.5 grams of ethane, what they are ignoring is the fact that you do have another reactant. You have oxygen. And if they do not mention oxygen, what they are assuming is that you have excess oxygen. Whenever you burn something, you usually assume you have excess of the oxygen. So if they don't mention the other reactant, we have plenty of it. But what happens if you're told how much of these two substances you have, your two reactants? Let's say that we're still burning the 2.5 grams of ethane, so that stays the same. But what we're doing is we're also going to be told that we have only 4 grams of oxygen. So instead of an unlimited supply, we have a limited amount. So how much CO2 is produced? So that's what we asked in the first problem. From the combustion of 2.50 grams of ethane and 4.0 grams of O2. Now, when we do this problem, what we're going to do is, or one way in which we can do it is do the problem twice. So just like we did in the previous one, we can say, well, how much carbon dioxide is produced by 2.5 grams of ethane? You go through the same calculation as we did before, and you come up with the fact that we have 7.32 grams of carbon dioxide produced from this amount. So we've already done the calculation. We know that 2.5 grams of ethane will go to produce 7.32 grams of CO2. That's done. But what about the oxygen? What happens if the oxygen limits how much is produced? How much could 4 grams of oxygen give us in terms of carbon dioxide produced? So what we'll do is we'll start off with that amount. Instead of starting off with ethane, we'll go ahead and start with the oxygen. We go through our series of steps. We convert this to moles. We do a mole-to-mole ratio. We want our moles of oxygen to cancel out. We want to go to moles of CO2. In this case, I'm going to go back up here to my coefficients. This might be a time where you don't want to throw in that 7/2, so we'll go ahead and use the second line. The ratio is 7 moles of oxygen will go to produce 4 moles of CO2. So 7 and 4. And then the last step is converting back to grams. And we end up with 3.14 grams of CO2. So what we have just done is we have found out that if we have 2.5 grams of ethane, we can produce 7.32 grams of CO2 from that. But 4 grams of oxygen is only enough to produce 3.14 grams of CO2. So in this case, with this, our oxygen is our limiting reagent. It runs out, and we can only produce 3.14 grams of CO2. I'm going to show you another setup. It's especially useful when we're trying to find out a lot of information about all of our reactants and our products. Now, when I do this, when I go through this problem, it's actually going to seem like a lot of work. It's going to seem like perhaps it's too much work to be useful, that you're not really going to want to use it. But later on this year, we're going to run into some problems where this setup is very, very handy. So I'm going to show it to you for this situation, the same exact equation. So we know that we have a 2 to 7 to 4 to 6 ratio. And we're going to go ahead and do the same problem where we are looking at 2.5 grams of ethane reacting with 4 grams of O2. Now, if we take the 2.5 grams of ethane, what we're going to do is we want to express everything in terms, we're going to use this table, we're going to express everything in terms of moles. So when the reaction starts, how much of these things do we have? We start off with 2.5 grams of ethane, which when you convert to moles using the molar mass, so we're dividing by the 30.07 grams per mole. I'm going to go ahead and fill this information in. 0.08314 moles of ethane is what we start out with. We never saw this number before because we never stopped in the previous problem, but we did convert 2.5 grams of ethane into moles before we did a molar ratio and went on. The 4 grams of oxygen, when you convert it to moles, dividing by the 32.00 grams per mole, gives you 0.1250 moles of oxygen. And at the beginning of the reaction, the reaction hasn't happened yet. We have 0 moles of carbon dioxide and 0 moles of water. We have not produced any of our products yet. So in the previous problem, or previous setup, what we tried to do was figure out, okay, which one was the limiting reagent? Well, we did that by saying which one gave us the smallest amount of product. Well, we want to determine which one's our limiting reagent before we even do anything yet. So the easiest way to do that is to look at the number of moles that you have and divide it by the coefficient. Think about what size of number you would get if you took 0.083 divided by 2. That gives us about 0.04. If you take 0.1250 moles and you divide it by 7, you're going to get a smaller number than you would if you divided this one by 2. So that's a quick way to determine that this one, the oxygen, is the limiting reagent. And we already knew that from the previous problem. It's the one that produces the least amount. So this oxygen is our limiting reagent. Now, here's another little trick that I like to use with this setup, is to decide how much are each of these going to change by. As the reaction goes on, we are going to use up ethane, we're going to use up oxygen, we're going to produce carbon dioxide, and we're going to produce water. And each of these are going to change according to their coefficients. If something has a coefficient that's large, it's going to change its amount by a greater amount than something that has a coefficient that's smaller. So since we've determined that oxygen is the smallest one, what I like to do is to figure out how much you're changing by is to find out something that I call a change unit. This is something that I made up. I don't know if anybody else uses this, but I call this thing a change unit. And so whatever this amount is, our limiting reagent divided by its coefficient in the equation is our change unit. If you take 0.1250 divided by 7, you find out that that is 0.01786 moles. So that is our change unit. Everything is going to change in this reaction according to this change unit, but it's going to be related to the coefficient. So the way this works is, this is our limiting reagent. It's easy to already say that this is going to be all used up, so it is going to decrease by that amount. Reactants are used up, and limiting reagents are totally used up. The ethane is going to be used up, but it is going to change by an amount of 2 times this change unit. So it is going to decrease by 2 times the 0.01786 moles. Our products are going to increase, so they're going to go up. And they're going to go up by, in this case, 4 times the change unit, which is 0.01786, and we're multiplying it by 4. The water is going to go up 6 times 0.01786. When I multiply these two together, if we're going to stick over at the water side, 6 times that is 0.1071 moles. It increased by this amount, so that is how much we have at the end. We're going to increase the carbon dioxide by 4 times this amount, and when we plug that in, we end up with 0.0714 moles. So at the end of the reaction, that's how much carbon dioxide we have. We have 0 moles of oxygen left. Limiting reagent, it's all gone. And this one, since we are dropping 0.08314 by 2 times this, so we're decreasing it by 0.3571 moles. In the end, we are going to have 0.04743 moles left over. Well, that seems to make sense because we ran out of oxygen. We expect to have some of our ethane left. Wow, that's a lot of work to this point. we've filled out this table. We know how much we started with. We know how much it changed by. We know that we have amounts of our products and one of our reactants left. The last thing, let's say that we are just going through and calculating everything possible. Let's say that they wanted to know how much ethane was left. So if we convert this 0.04743 moles back into grams, the molar mass, remember, was 30.07 grams per 1 mole. So you multiply that, and you end up with 1.43 grams of ethane. That is the ethane that is left over. We have 0 grams of our oxygen. Our 0.0714 moles of CO2 is the equivalent of, when we convert it back, the equivalent of 3.14 grams of CO2. Oh, where did we see that before? Well, that's what we calculated. If we use up all of our oxygen, our 4 grams of oxygen, we were going to have 3.14 grams of CO2 produced. And the very last one, which was one that we never talked about before, but if you have 0.1071 moles of water, and you are to convert it back into grams, the molar mass 18.016 grams per 1 mole, you produce 1.93 grams of water. Okay, this is kind of a, I know it's been a long process, but I like to tie this whole thing up at the end, and I find this kind of cool when you think about we did all this work, we did a lot of math here, and when you look at this, when you have 1.43 grams of the reactant left over and you produced these amounts, when you add all of these up, you get 6.50 grams total. What did we start with? 6.5 grams of our starting reactants. Law of conservation of mass, we expect to end up with the same. So there you go. Okay, so we just went through a whole bunch of calculations. We were doing really just one problem, and I showed you several different ways of doing it. If it is a simple stoichiometry problem, please just do the way we did it at the very beginning. Keep it very, very simple. There's no reason for you to go through and do a very, very complex problem. Don't set up a table if you don't have to. So I hope this helps. And again, stoichiometry problems, largely being successful means going out and doing a lot of practice. So have fun.